Hi guys. Okay, so let's look at the first law of thermodynamics. First law of thermodynamics states that energy cannot be created, energy cannot be destroyed, but energy can be transferred from one form to another. So what are the different types of energies that we know of? We know potential energy, by virtue of which substances remain at rest. Then we know the kinetic energy, by virtue of which substances move. Then there is mechanical energy, sound energy, heat energy, light energy, electrical energy, chemical energy, atomic energy, nuclear energy, and then there are so many more types of energies. But we're going to focus only on the heat energy and the chemical energy because we are looking into thermochemistry as one of the other disciplines of chemistry. So what do we study in thermochemistry? We study the amount of heat that is absorbed or the amount of heat that is released in a chemical or a physical transformation. Okay, but why is there a need even to study this? So the concepts that relate to the thermochemical principles are being used in a variety of scientific and technical, applications. For example, in food industry. In food industry, the food scientists are constantly studying the amount of energy that is going to be released from a certain food type. Biologists who are studying the biochemical reactions are all the time trying to figure out how much of the energy is released when a certain food type is metabolized, right? Now, the scientists who are working in the transportation industry are looking for alternate forms of energy. And engineers are constantly working on bringing those machines that can make the surroundings more efficient. And that's where the energy plays a very important role. All right, so now let's look at the first law of thermodynamics a little bit in more detail. So just wait for me here. All right, so as you can see this diagram here on the screen, the first law of thermodynamics we talked about is where the total energy of the system is conserved. Okay, so let's try to understand a little bit more about this relationship of work and energy and so forth. Okay, so energy, what is energy? Energy is the capacity to do the work. Okay, so the capacity to do the work is energy. Next is what is work? Work is the process of causing the matter to move. So as scientists, as basically as chemists, we are interested only in matter, right? We're studying about the behavior of matter. So when the matter moves or there is some kind of change seen in the matter, that means some kind of work has been done on that matter, okay? Now, let's look at one case in which the matter is the gas. All right, so what is happening or what is the gas doing? Work done by the gas or the work done on the gas? So we have these two cases in which the work is being done on the gas, and the second case is in which the gas is doing the work. So we have enclosed the gas in a cylinder and we have a movable piston on top. And what do? We apply pressure on that piston. Now piston is a surrounding and the gas is our matter and gas is the system. Okay, so what happens when you apply pressure in the first case, when you apply pressure on the system, what happens? Pressure, as you see, is the force over area. So the piston begins to move down, and as the piston moves down, the initial volume now becomes smaller, and now the final volume is smaller. So the situation moves from the diagram A to a diagram B, where we see the gas is now in a compressed state. So case one is really a state of compression. Now let's look at the case two, where the initial volume is small and now the gas is the one that is pushing the piston up. And as a result, the gas expands. So that is the case 2. So in the case 1, we really see the surroundings are doing the work. Okay, the surroundings are doing the work, and in that led to the situation of compression. In the second case, it is the gas that is doing the work. In other words, the system is doing the work. So when the system is doing the work, then the system is pushing the piston and the gas expands. So we see expansion. Okay, so this is a very simple explanation of this diagram. Now we are going to quantify the work. How much of the work was done by the surrounding or by the system? So how do we do that? So here's the thing. We know that pressure is equal to force over area, right? And what is work? Work is the force that is applied over a distance. Okay, so can you write work like this? That W is equal to force times distance, and from pressure is equal to force over area, we can have pressure times area is equal to force. So these are just simple algebraic transformations. Force is equal to pressure times area. So can you substitute pressure times area instead of force in place of force? Yes, times D. Now, in reality, what is this D? The D is delta H. That is the change in volume, basically. Okay? From expansion to compression or compression to expansion. So we can write this pressure times area times delta H. Delta H is that change in height in the cylinder, delta H. So area is equal to, area times delta H is equal to change in volume. Okay, so now we have pressure times delta V. So our final formula for the work becomes pressure times the change in volume. So this is our final way to determine the work. Now here, since we are talking about gases, then yes, the pressure and the change in volume, that relationship comes into play. But let us just try to understand things in a little bit broader perspective. So from a broader perspective, it's really who's doing the work, right? Is it the system doing the work or is it the surrounding doing the work? So from the point of, if the gas is looking, the gas is the system. So when the gas is looking, who's doing from the perspective of the gas? If the gas is doing the work, fine, it's expanding, fine, it likes to expand, but it has to do the work. It has to push the piston. And when it's doing that, gases don't like that. Our systems don't like that if they are the ones to do that work. So keep that in mind, that from the chemistry perspective, from the chemists, the gases are lazy from that perspective, okay? Or systems are lazy. Our systems that we deal with, or chemical systems rather, you can say that. Chemical systems are lazy. And when they are lazy, then what's the deal with them? This is the reason why you see this here, the W is negative. W has a negative connotation to it. So anytime from the point of view from the chemist, the system is doing the work, it has a negative value. So with that said, the formula here now is W is equal to negative P delta V. So in other words, anytime the gases are expanding, the formula you're going to use is W is equal to negative P delta V, because our chemical system, from the chemistry perspective, they are lazy. They don't like to work. So negative. Although the volume increases, okay, yet the value for W is going to be negative. On the other hand, when the surroundings, we like the surroundings to do the work. In other words, the scientists, the systems, the chemical systems enjoy the surroundings to do the work for them. So the value of W is, from their perspective, it is positive. Okay, although you see the compression, but but that's where the change is going to happen. Just think about it. Carbon dioxide, just by itself, nothing happens. But the moment you put the carbon dioxide in a box and you push, apply pressure, and it's then that's where the carbon dioxide in a gaseous state begins to, converts to a solid state, and that's like it. So when the surrounding did the work, only then the transformation was seen. Okay, so that's the thing with the, from the chemist perspective. Now, there are two people who work with the energies and the work and all that stuff. There are two, scientists and the chemists. Now, here's the thing. Scientists are system centric because our systems for us are the chemical reactions. Engineers, on the other hand, are surrounding centric. Now, what does this mean? This means, now look at it from the perspective of engineers. The engineers are the ones who make the machines, and these machines are the ones who should be doing the work, because we want to make the surroundings efficient. What is the surrounding? To be human beings. When the machine breaks, we human beings go to fix the machine. So if we are doing that, it is not a good machine. It's not, there's no efficiency there. So that means that it is not seen in a good light. You can say that. Chemists, on the other hand, surroundings should be doing the work. Our apparatuses should be working. When you set up the heat in a chemical, to start a chemical reaction, that heat, that certain temperature, you put it in a cooling bath, there should be a certain temperature. You're trying to apply a pressure to make certain things work, some reactions work. Yes, all those outside thing that is done, the labs, the apparatuses, the test tubes, the stirrers, the hot plates, the ovens, distillation apparatus, and all those different apparatuses should be doing the work for the chemical reaction, for the molecules. So keep this in mind, that the atoms, molecules, lazy folks. Okay, so they want the surroundings to work for. So that's one thing with them. So with that said, we will have two types of formula here. The way the systems, the first law of thermodynamics. For the chemists, the first law of thermodynamics is delta E, that is a change in energy, is equal to Q plus W. This formula is for the chemists, but engineers, they are going to look at it from this perspective. Delta E is equal to Q negative W dash. So when you do a Google search, or all these other, sometimes some of the books, they write this. So what they say is that Q plus W and Q minus W dash, there's a difference in that, and that difference is the point of view. Who's using it and from what perspective? Okay, so now let's look at the point of view of the system moving forward, because we are working in this is for the chemistry, folks. So here for the chemists. Now, E is equal to, this is a first law of the definition of the first law of thermodynamics, basically is, the total energy of the system is conserved. Those things we know, that energy cannot be created, cannot be destroyed, but it goes from one form to another. So those like standard things. But from now, we are really trying to look at things a little bit more deeper, that internal energy of the system. Can you bring a change? Yes, you can change it by the work, and you can change it by the amount of heat you're supplying. So the total energy of the system is, yes, conserved, but at the same time, it is the delta E is equal to Q plus W. So we can change the internal energy of the system by the work and by the heat. Okay, so let's look at heat now. Heat is Q. So again, the heat will have two values. Q can be positive and Q can be negative. Okay, so Q is positive in the case of endothermic reactions. Endothermic. Now, what kind of reactions are those? Endothermic reactions are those in which the heat flows into the system. The flow of heat flows into the system. Okay, and Q negative is exothermic. And what does that mean? Exothermic reactions are those in which the heat flows out of the system. Okay, so it's basically the direction of heat. Heat flows out, and then it's all into from the system. Basically, that's more important. So what is the direction of the heat? Into the system, and I'm going to just put this here, into the system. Sorry, into the system, and here we have heat flow out of the system. Okay, that's one thing about the Q plus and the Q minus. What about W? W, as we already looked at it up, we see that the work, it is defined from the point of view for us. The work is the point of view is always going to be the system for the chemists, and this class is for the chemists, but engineers are welcome too, no problem. Okay, anyway, so here we have a scenario. Now let's look at the flow of work here. Okay, so before we get into that a little bit, I want to do work. Okay, let's look at this from the point of view. Okay, here, system, going from a system, when the energy moves from the system to the surroundings. Okay, the energy, this is the flow of energy from the system to the surroundings. So what is the situation? System is going from the energy is going from the system to the surrounding, and then another is, one minute, and the other is from the surrounding to the system. Both the way, from the surroundings to the system. And again, this is the flow of energy. Okay, so in the first case where the energy was going from the system to the surrounding, that in that case the W is negative. Why? Remember that expansion of gas. Just keep that picture in mind. And gases are the ones who have to do the work, and they're lazy, they're not happy in pushing the piston up. Okay, that's one thing. Next is when the surroundings is giving heat to the system, systems are happy. That means your stir bar is working, the test tubes are intact, the heat, the definite amount of heat that was needed to be supplied, that is working, and whatever the setup was for the apparatus in the experiment, all that is just working fine. So reactions are very happy, right? So here the surroundings are the ones that are providing the heat to the system. So not just all the time it's about gases, chemical reactions could be liquid and solid state, liquid state, so forth. So here we see that the sign of W is going to be positive. Okay, and in this case we have seen the compression. So just keep this in mind, that compression, although gases don't like being compressed, but at least they don't have to do the work. That's the thing, so we're in the terms of work from that perspective. All right, now on the other hand, so once again I just want to reiterate that this is going to be negative P delta V, and this one here is going to be positive P delta V. All right, now let's look at the scenario, the flow of heat. Okay, this is a situation where you have a hand and you have the ice on the hand and the ice is melting. Okay, so now what's happening here? Your ice is the system in the first case. So let us say this is case A, this is A, and this is B. Okay, so what's happening here in the case of A? In the case, ice is the system and the hand is the surrounding, right? The ice is melting. Why is it melting? Because it is absorbing the heat from the hand, right? And what's happening here? Ice begins to melt. The hand is losing the heat. Hand begins to feel numb, right? So in that case, what happens? Now system, here the ice is the system. So what happens? The internal energy of the system, and the system in this case is ice. So what is happening to that? It increases, okay? It increases. And when that happens, what happens? Because obviously the ice is melting. When the ice is melting, that means it's absorbing heat from the hand. So the Q, the internal energy of the system, also increases and becomes positive. So it's absorbing heat, in other words. So here, heat is being absorbed. So anytime heat is being absorbed, the value of Q is positive because the internal energy of the system is increasing. Q is what? Q is heat. So the heat is increasing. So Q, I'm going to just put it here. Q is the heat. Okay, so the heat of the ice increases. That is why it begins to melt. Now let's look at the next scenario in which ice is the surrounding and the hand is the system. The direction of the heat flow is still the same from the hand to the ice. And so what happens? Fine, the ice is going to melt. But now what is happening? Your system is the hand. So when you feel numb, that means that the internal energy of the system, which means your hand, is going to go down. Okay, hand, because, and you can feel it, numbness in the hand, right? If you have ice hand on your hand for too long, your hand becomes numb. So that's lost some heat, some energy there. Okay, so what happens to the heat? Because in this case, it is the system that is giving away the heat. Remember that. So the Q, the heat is being released by the hand. So here, the heat is being released by the hand. So in this case, the Q was a positive number. So here, the Q becomes a negative number. Okay, the Q is negative because, just put this in one line. Here, the Q is positive when it's being absorbed, and the Q is negative when it is being released. So the ice melting is a positive, but the ice, on the other hand, I mean, the Q is positive when the heat is being absorbed from the hand, and Q is negative when the heat is being released from the hand. So these are the two things, okay? So this was our understanding of the first law of thermodynamics. And now in my next video, I'm going to be doing the calculations, the mathematical problems that involve the use of delta E is equal to Q plus W, this equation. Okay, so I'm hoping that this theory that I tried to explain from the first law of thermodynamics, I hope it was easy. And yeah, I would just say the best way to learn it is to sometimes take some pictures in your mind and then just stick to that, and then it works. Okay, so there's no confusion between system and the surroundings then. All right, so I hope that was easy, and thank you for watching. Bye-bye.